Russ, and thank you everybody for being here. Before we dive in, we have a couple people here from the company as well. So Tanya, as well as Ian, who just joined the company this week. So we're a rapidly growing company. We're excited to be here. Also, before we dive in, a couple of logistical things. So I actually have a question for everybody that I would love your opinion on. So I'm going to have this coming around throughout the presentation, if you don't mind filling that in. And then we're a small group, so if you want to ask questions, please feel free to interrupt throughout the presentation, ask questions as they come up rather than waiting until the end. So as Russ mentioned, I'm going to take us through the first half of the agenda. We'll go over the company briefly. I'm going to talk about the customer pain points that we started out solving, talk about the commercialization process that we've gone through for this disruptive technology, and then I'll hand it over to Andrew. He'll talk about gas chromatography with flame ionization detectors, as well as some pretty cool case studies using our new technology, which we call the Polyarc reactor. Before we dive into the content, we know that we're filling some pretty large shoes. So we know the original topic for February was medicinal marijuana, and everybody was excited to learn more about that. So we've actually, some of the case study data is analyzing cannabinoids using the Polyarc reactor. So you have to hang tight for the end of the presentation, but know that we're getting there eventually. So as Russ mentioned, we were founded over a year and a half ago now, so July 2014, and the vision of the company is to improve lives through the use of catalysis. So as a company, our vision is to continue coming out with new products, but the through line through everything will be they all use catalysis. That's really the bread and butter of what we do and what we specialize in. You'll notice there's a lot of University of Minnesota ties here. We feel very fortunate to be in a state that has such great chemists and chemical engineers and companies that are headquartered in Minnesota that are great innovative scientists. So we're growing the company and we have a really great talent pool to pull from here, which has been fun. I'm going to talk about the first product, our flagship product, the Polyarc reactor, and we're out of Eden Prairie, Minnesota. So we're a local company. We have an office out there where we do a lot of the manufacturing of the product, development, things like that. We have our own lab and everything. So when we think about what scientists love to do, there's a lot of scientists that are in research and development, but a lot of scientists might love doing research and development in the lab all day. When you think about building a company, you actually need to sell products in order to build a successful company. So typically, in order to sell something, you need somebody that wants to buy it, and in order to want to buy it, you should be solving some sort of pain points that they might have. So the reason that Paul Downhauer is up here is he's actually a chemical engineering professor now at the University of Minnesota, and the original concept for coming out with a product like the Polyarc, which we've developed, came from Paul and students in his lab. So him and his students were trying to analyze the products of cellulose pyrolysis down here, which is really a fancy word for what happens when you heat things. In doing so, he was using GCFID to analyze this chromatogram, and you can see there's hundreds of different compounds. So in order to determine where all the carbon from the cellulose went, they needed to calibrate every single peak and find response factors for every peak in this chromatogram. So if you've done calibrations before for GCFID, you probably are already realizing what those pain points might have been for Paul and his students. It would take hundreds of calibration standards, hundreds of calibration curves, so really they needed a better way to do this. It would take hours, months, there might even be a PhD that spends his time trying to quantify everything that's in that chromatogram. So what he said, and then what we were able to take and develop into a commercial technology is, how do we develop a product that helps with this and that solves the problem of having to create all of those calibration standards and calibration curves? So that's what we are doing. So moving into how we've actually brought this product to market, when you think about a disruptive technology, two things, and really a technology in general, two things that are very important and need to be true. One is you have to develop a great product. The second is you have to develop and execute a great marketing and sales plan, and it's not just to launch the product, it's the ongoing plan for how do you penetrate certain markets, how do you actually find the right markets. So when you think about developing that great product, there's a series of steps that you go through. The one call out here is this rapid iteration and prototyping. So when you think about doing in-house development, rapid prototyping in-house, but then getting to a point where you want to engage your pilot customers, it's this loop here of you learn something in the development cycle, you make changes, and then you learn more, and you just continue to iterate here until you're ready to launch the product. The great thing about being at a small company is that can happen very quickly. There's a lot of bureaucracy that's removed. As Russ said, I came from a very large company, so I'm familiar with the corporate structures, and even at medium-sized companies, there's just hoops that you have to go through, where when you're at a small company, you get to make all the decisions and you're able to make changes and incorporate feedback very, very quickly, which has been helpful as we've launched this product. When you think about developing the launch plan, you really need to understand and do market research to know where are you really going to focus. So in our case, it's who has the most FIDs, who's even using FID, what are the local companies that use FID, and then outside of locally, who are those companies that don't just have 4, they have hundreds of FIDs, they have thousands of FIDs. You have to think about regulations, so there's companies that are EPA regulated, there's companies that are FDA regulated. You really have to be selective with where are you going to get those earliest adopters first and focus your attention there, because again, being a small company, you don't have the resources to investigate everything. You have to be very focused and intentional with your time. So that moves into this part, which is finding the early adopters and industry champions. We'll talk a little bit more about that, but applying the change adoption curve, which may be new to some people in the room, and we're going to talk more about it, but using that logic to find the right people at the right phase in your launch plan has been very important for us. So again, being in Minnesota, we have a lot of great chromatographers, some of which are in this room, that we've been very lucky to be able to learn from and learn more about chromatography, which again, our specialty is really catalysis. So learning from those industry champions and industry experts has been great. And then just making sure that you have a multifaceted plan. So there should be a digital presence, a physical presence. You're going to be at some trade shows talking to people, especially at the beginning when you're trying to help people understand and learn what the product actually does. It's new. So putting it on a website and trying to sell it and having that be the only vehicle isn't going to work very well. You have to find people and talk to them. You need to go present at different conferences and trade shows. You have to come out with publications that show and prove the data works using our device. So really having that multifaceted approach. The important thing that I want to note before moving on is while these look like they're 2 siloed processes, they actually happen back and forth. So again, being at a small company, it helps out a lot, because as I was working on learning more about the market, I would learn something and it would help inform what type of data Andrew might be generating, or we'd find a group of pilot customers and then we'd learn quickly, and I might even shift over to doing the engineering. You saw I have a background in chemical engineering, so when I started, it was really hands down focusing on developing the right product. So I spent a lot of my time doing that as opposed to going to different trade shows. And so you're really able to bounce back and forth and do both of these in tandem. So what I'm going to spend a little bit more time on are these 2 sections. First off is this product testing and prototyping. So when we think about the in-house development that was done, if you look at the original idea, whoopsies, we developed a product that did what we needed it to do in that, and Andrew's going to talk more about what our product does, but conversion of all organic compounds to methane. That's what our reactor does. This product did that and did it pretty well, but we quickly realized that there was optimization that could happen before we even really started engaging those pilot customers. So as I mentioned, our expertise is really reactor design and catalysis. So using 3D printing, this is plastic 3D printed, but we were able to develop different models, test different internal geometries extremely quickly. We have a 3D printer in-house, so we were able to develop a new model, print it, test it, and develop the right catalyst metals, but also catalytic support that would go inside of this reactor. So the goal with moving from this boxy design, which again converted organic compounds to methane, to this small catalytic reactor, and I'm actually going to pass it around. This is what the reactor is. It's an older version, but it does the trick. Was to optimize the catalytic support so that we would maximize conversion to methane, and then also minimize axial dispersion within the reactor, because we learned from some people in this room the importance of eliminating as much dead volume as possible, and we wanted to make sure that we got rid of as much dead volume as possible. So once we optimized that portion, again, in-house, we had a product that we felt we could bring to pilot customers. So what you'll notice is this reactor cartridge is actually this metal 3D printed, which is what's being handed around right now. So we print the cartridge using stainless steel 3D printing due to needing to get the right internal geometries within the reactor. But we basically, the heart and soul of what we're great at stayed the same. We kept that internal reactor design, catalyst support, all of that stayed the same. And we then developed a set of GC connections. So we had flow control, we had different fittings that would connect to everybody's GC column and then also feed up into the FID. We had an enclosure. This reactor runs really hot. It runs between 400 and 500 degrees C, so we have to insulate it and enclose it in something. So we had an enclosure. And we felt great and we felt ready to go to pilot customers. But again, the importance of learning from those pilot customers, finding a need and them saying, okay, minimizing dead volume is a huge priority for us. It's clear to see when you look at the actual commercial product that we brought to market in October. So we launched our commercial product in October and we began selling. It looks a lot different than the pilot design that we started with. So when you take a look at the pilot design, there's a lot of fittings and there's a lot of metal tubing which introduced dead volume. As we learn more about the importance of eliminating those fittings, I mean, you can have leaks that are introduced, dead volume broadens peaks. We evolved to a design over here where you can see the inlet and outlet of our reactor are actually capillary metal tubes. The one you're holding is an older version, so that's not the capillary version. It's harder to transport and not break the capillary version when you hand it around a group of people, so we didn't bring that one. But we connect to the column with a zero dead volume union. We feed the outlet of the reactor up into the FID with capillary metal tubing. So it's almost like you're feeding a GC column into your FID. So we learned from our customers how important that was going to be. The enclosure changed quite a bit. So that looks a lot different from the box that we had over here. And it actually fits right into a detector position. So it is mobile and can go multiple places on a GC. But a lot of our customers have a yeah, I agree. That was an important move. We felt strongly about that one too. It fits right into a detector position, and I would say 90% of our customers make a detector position open or available so that they can have it fit right into that, and that was important. This one, the GC oven top, couldn't close. And we said, maybe some people will, maybe they won't, but it was really important for them to have the GC oven closed. So we designed something that allowed that. It's a little tough to see, but here, looking at the inside of an oven, it hopefully looks very similar to what you're used to seeing. There's just a dead volume union that connects to the inlet, and the outlet feeds right up into the FID. Again, we got rid of all of these extra tubes, so something that we learned. And then the last thing is add-ons. So this is our electronic flow control module. But as we had more customer needs come up, we would develop an add-on. So for example, not everybody uses Agilent. While they might have 80% of the market, they're not the only GC manufacturer. So this cable assembly was designed to plug into an Agilent GC, but what if they don't have an Agilent GC? So we developed a separate heater control that is a custom part that we work with somebody to produce, and it allows them to supply heat to our reactor. So it can go on any types of GC. We have customers that use PerkinElmer, we have customers that use Shimatsu. So really making it a true universal carbon detector that can be applied to any FID that's out on the market right now. So that's a little bit about the pilot program. I'm now going to talk about what is this thing, change management, that she's talking about, and why is it even important? So having a change management strategy and finding early adopters and industry champions is actually essential when launching a disruptive technology. And if it's done well, the thing about it is nobody even knows it's happening. That's the kind of secret behind change management, is if you do it well, you don't even know that it's happening because it just feels natural, which is what's great about it. So let's take an example that hopefully people will be a little familiar with. Does anybody in here remember using this thing or using a typewriter? Yeah? Okay, good. If you don't remember a typewriter, maybe the early days of personal computers is a little bit more familiar. But if you think then about where we are now with laptops, smartphones, tablets, imagine if when you were using this typewriter, someone came up to you and said, okay, you immediately are now going to start using this. The days of using this to type different things, you actually use this to do that now, and you also connect to the internet, you can communicate with people in different countries at the same time. Like, how would that have made you feel at that moment? So keep that in the back of your mind as we talk about the change adoption curve. So this is the change adoption curve, and it's broken out into different segments. And really what we'll walk through, there's different groups of people that feel different ways when they need to adopt a new change or adopt a new technology or go through some sort of change in how they're doing things. So the typewriter example is, depending on how that made you feel, you would fall into one of these different buckets. The first are the innovators. So these are the people that create the pressure to change. If you remember Paul Downhauer from the example earlier, he's an example of an innovator. He said, I have a problem, I'm going to develop a solution to actually solve that problem and create a change. The early adopters are next, and these people are willing to consider how this change would make things better. They are excited about how it will improve the way they do things now, and their opinions are actually very well respected by all of the other people that come later in the change curve. An example here would be the pilot customers that we worked with. They're usually pretty excited about new technologies. The next big group are the early majority. So these people, they really need facts, and they deliberate things before accepting the change. They want to review all of the data. They look to the early adopters as role models for whether or not they should start moving to that new technology. And then you move into the back half of the curve, which starts with the late majority. So there's quite a bit of skepticism that come from these people. They don't adopt the change very quickly, especially until, over half of the people have already moved to that. And then the last group are the laggards. So these people really cling to the past, and they view change with distrust. So the reason that they would stop using a typewriter is because theirs broke and they can't buy a new one. They have to buy a new personal computer. So there's no right or wrong answer, and it's great to have all different types, but you can imagine that when you launch a new technology, if I was to focus all of my time, or we were to focus all of our time here, it would take us quite a bit of time, or we would never be successful. So you have to be very strategic with how you engage the different groups. So why does this matter to us? If we look at the evolution of the GC, let's take the 5890, compare it to the 7890, there have definitely been some changes. There's aesthetic upgrades, and auto sampler, which isn't shown, has been added. They've moved to mostly capillary columns, and there's been improvements to the GC, but the core function remains the same. And in fact, we work with a lot of people that have hundreds of GCs in their lab, and they use 5890s. And they do that because they still work, and they still work really well. So there hasn't been a need, and that's great. The thing about the Polyarc is we actually have developed a technology which we see as a disruptive technology based on, as Andrew is about to share with you, some of the problems the industry has been able to solve now and see with the FID that you've never been able to solve before. But the beauty is it works across all different gas chromatographs with flame ionization detectors. So we work with 5890s, we work with other GC manufacturers. So while we still apply change management in the change curve to figure out how we're going to get adoption in different industries, it's great because, like I said, these are both very prevalent instruments in the industry. Also, just very quickly before we move on, we've been excited about the awards that we've gotten in the press and publications. So national and actually international awards. The Analytical Scientist had a set of international awards called the Innovation Awards. The Gulf Coast is a big conference that happens down in Texas every year. We won the Best New Product Award there. Multiple articles, so some local but also national publications, press releases by people such as the Department of Energy, and then peer-reviewed publications. So the Analyst that just came out, we have a publication there that came out of Paul's lab. And then also American Laboratory, I believe, is something that people in this room are probably familiar with. In the January-February edition, there's a pesticides article in there that uses the Polyarc to do quantification. So that's on newsstands right now, but there's more on our website. So if you check out our website, you'll find a lot more app notes, publications, things like that.
Unlike Kim, I have zero business experience, so I hope she gave you an idea of how important business experience is in a startup, even at the really early stages when we were prototyping. Having Kim there and going to the customers, iterating back with prototypes and information, we did that a lot, and that really allowed us to get the product that I'm going to show you right now. So, and we're pretty happy with it. So, first, what I want to do is go through a little bit of the basics of GC, or gas chromatography. and the FID, how it works, how can we actually improve that technology. Go into our reactor technology, and then finally end with some case studies that look at what this device can do and what it has done for some of our customers. So the gas chromatograph is about 60 years old. Here's the 5890 from Agilent, who was Hewlett-Packard at the time. And how does it work? This is actually the most common way to separate and then analyze mixtures of components, organic components. Well, the way that it works is pretty simple. You inject a mixture of chemicals, so I'm calling them A, B, and C. And when they get injected through this hot injector, you start to separate them through this column, which sticks to the molecules differently, right? So some of them move faster, some of them move slower. By the time they get to a detector, they're separated, so you get isolated peaks, hopefully, if you've done it right, that give you some sort of quantification of the compounds. Now, the issue, of course, is that these detectors are not similarly sensitive to all the molecules that you send in there, which is why we have to calibrate the detector for response factors and do the calibration curves and things that we all hate to do because it takes away from doing the actual science. So why do we have to calibrate? Well, the FID is actually the most common detector used for gas chromatography, and that's because it has a long linear range. It's like 6 orders of magnitude, linear range, orders of magnitude, and because it's sensitive to carbon molecules, which make up so many things that we care about. And the FID is also painfully simple, meaning that it's easy to fix, it doesn't break that much. And the way that it works is you actually just send a sample into a flame that's burning from the mixture of hydrogen and air. And when you burn that sample, you create these CHO plus ions, which is the prevailing theory. They're still not 100% sure. And you create those because you have this potential, maybe 200 volts, set across that flame. And when you create those ions, you have to balance that with an electron. And so you count the electrons that flow here to balance that current. And then the number of electrons that you make are proportional with some proportionality constant to the amount of sample that you make. And it's estimated that about 1 out of every 1 million carbon atoms form a carbon cation like this. And of course, that probability changes based on what sort of carbon functionality you have.
So indicate that integrators now just go by areas.
Yep.
So they're not calibrated.
They're not calibrated, correct. So the peak area that you guys are used to is the integrated detector signal that you're getting. So that's, you're measuring electrons versus time, and you're just integrating that full signal, which is a peak. So that's the area that you get, which is a picoamp. So it's an ampere. It's the number of electrons times the x-axis, which is the minutes. Yeah. So was there another question in the back, or you guys? Okay. Yeah, definitely stop me as I'm going. Some of this will be new. So how does the Polyarc reactor change this whole setup? Well, I'm going to put them side by side. So everything else is the same. We inject our sample, A, B, C. And for the purpose of this, I'm assuming that A, B, and C are different molecules but have the same amount of carbon. So they get separated, but now when A gets to this Polyarc reactor, we convert it to M, which is methane. And now when M goes to the FID, it burns. We convert B to M. That burns with the same efficiency as the previous M. And so now we have peak areas that are all the same. So it doesn't depend on the identity of the original ABC. We've converted them to M so that the sensitivity is the same in the flame ionization detector. So it's a pretty simple concept. The trick is, how do you do this magical black box chemistry to convert anything with a carbon atom into methane? Well, luckily thermodynamics is pretty kind in this sense, and we can create some good catalysts to do this chemistry. And I'll talk about that in a little bit. Any questions before I go on with this? Yep.
Does the ratio of the response to the FID to the Polyarc tell you how much oxygen is in the compound?
Sort of. So it would tell you, that's a good point. So anytime there's oxygen, you're going to get a reduction in signal. So if you looked at the ratio between these two, it would tell you how much heterogeneity you have in some sense. I don't think you could quantify it because
Not really useful.
yeah. I mean, it would be useful to know that that's an oxygenate peak, or that's a, it might be a nitrogen. It might have a nitrogen or some other heteroatom. If that's what you're interested in, yes. Maybe you have a gasoline sample, or maybe we're looking at renewable gasoline and there's oxygenates in there, and you want to know which peaks are oxygenates, and you don't have a mass spec. This could tell you that. So that's an idea. Yeah. Good thought. Okay. So what does this mean for your analysis? Well, let's say we want to put carbon monoxide into this flame and try to analyze the amount of that compound. Well, if you guys have used GCFID before, you know that that won't work because CO won't burn in this flame to produce CHO ions. So the signal you get is actually zero. You don't see any carbon monoxide, even though it has a carbon atom. However, when you put our reactor in there, and this is similar to a methanizer in this case, you're converting everything to methane, all the carbon monoxide to methane, and you get a signal that has the same response factor, same sensitivity as methane would in the FID. And you can repeat this for a number of other heinous molecules that don't react well in the flame ionization detector, such as carbon monoxide, carbon dioxide, formamide, formaldehyde, formic acid, and there's many others. And you can see that the response of the Polyarc is all the same, and the response of the FID is abysmal. Some are invisible, some have very low responses. And this is because we're converting all of these molecules on a carbon basis to methane. So what is this Polyarc reactor? Well, Kim's shown you a few pictures of this with a stainless steel reactor that we've passed around and has our proprietary catalyst inside of there. It also has some channels in there to provide the volume and the area that we need to do the reactions. It sits on top of your gas chromatograph in a detector position or elsewhere if that space is filled. And what we do is a simple two-step reaction. So we take all the column effluent and we pass it into the first chamber of this system, and we do a combustion reaction with air. We're at a high temperature. Everything wants to go to carbon dioxide, all the carbon. And then everything else, if it's hydrogen, will go to water, and other species will get oxidized. And then those go sequentially to another step where we actually add a lot of hydrogen to push thermodynamics. And we do a reduction step to convert everything to methane. And we see over 99.9% conversion of methane to methane. So we have these proprietary catalysts, and we also take advantage of the fact that thermodynamics are favorable to methane in certain conditions of oxygen, carbon, and hydrogen ratios. So this is a ternary plot, and basically it shows you in 3 dimensions at what oxygen, hydrogen, and carbon ratios will you form methane favorably according to thermodynamics. And this is 99.9% conversion to methane in this gray shaded area at different temperatures. So we're tuning all of these parameters, temperature, composition, concentration, to get methane for all molecules that would go into a GC and almost all concentrations.
What happens to the oxygen?
To the oxygen? Yep, so in the second step, any residual oxygen will get converted to water. So you'll have water coming out of your FID jet, which you make water in your FID as well.
It doesn't affect the signal?
It doesn't, no. If you do too much air, you will blow out your FID flame. Yep. We've done that. That was an iteration. So the beautiful thing about this and about thermodynamics and combustion chemistry is that you can do it for any and nearly all molecules. So there's something like 6 million organic molecules. We haven't tried all of them, but we've tried a good number, and some of our customers have as well. So this is just a snapshot of some of the odd and fancy ones. You can see there's a lot of silicon in here, inorganic compounds. And these represent a number of different industries, from cosmetics to pharmaceuticals to foods and fragrances, commodity chemicals, carbohydrates, renewable fuels, those types of things. So it is a pretty versatile device, and we've been blessed by thermodynamics in this case.
What happens with a fluorochemical?
Yep, so we can do fluorine. When you reduce it, you'll probably get HF, so you don't want to put your mouth over the flame. But if you vent it, you're fine. I mean, you're just making HF as you would when you combust it in the flame. It will, yep. Yep, halogens. Sulfur is a known poison to catalysts, which people are concerned about, but we can do sulfur. We can do inorganic compounds, or inorganic derivatized compounds with silicon. There isn't anything that we found that we can't do yet. So I want to go through the 3 real benefits of using the device and give some key examples. You've already seen that we can see CO and CO2. I wanted to show you the chromatograms. So here's a sample of, it's a gas mixture, a gas cylinder of CO, methane, CO2, ethane, ethylene, and helium and hydrogen. In an FID, you see, we don't see any CO and CO2. There's just no peaks, no signal. When you use the Polyarc, you see a signal for both of those, and the areas, if you were to integrate these, are the same as methane, and 1/2 of those of ethane and ethylene, because they have 2 carbons. So it's on a per carbon basis. We also show, so for formic acid, which is a common food additive and is particularly difficult to analyze with a lot of analytical methods, if you were to put it into an FID, you would see a teeny little peak right here. And this is relative to DMSO, so again, a sulfur molecule. And you can see as you increase the concentration, if you were to assume a response factor of 1, you'd be getting 0.8% of what you actually are sending in. Whereas when you use the Polyarc reactor, you have a sensitivity that's linear over a long range. You have response factors that are equivalent to 1 with respect to DMSO. So you no longer need to calibrate. You have an internal standard, and you can take the areas and the ratio of the areas and get exactly the amount that you put in out. We also drastically increase the accuracy of your analysis. And this is in part because we remove a lot of those steps where a lot of error can be introduced. But it's also because response factors are notoriously hard to calibrate for. A lot of people, when they look at a straight alkane, and I've done this in my grad work, was we assume that the response factors are all 1 on a per carbon basis. And they are pretty darn close to 1. But I wanted to show you this example because you can increase the accuracy even for these cases. So this is a C5 to C18 N-alkane mixture. And you see when you assume a response factor of 1 using just an FID, you get errors between 2 and 10, maybe 11%. And that's because the response is actually slightly different because those carbon atoms are burned slightly differently in the FID. When you use the Polyarc, now your accuracy is in the 1% range, which is probably similar to the error in making that sample and also injecting it in your inlet, and the inlet discrimination that can occur. We also drastically reduce the time of your analysis. So I'm going to show you the gold standard of a 5-point calibration, which I know no one in here does, and I've never done until I did this. But this is the right way to do it, and I wanted to show this because this is a comparison that will demonstrate that we can reduce your time even if you're doing the best of the best analysis while increasing your accuracy. So let's say you're looking at a 9-component mixture and you want to do a 5-point calibration for each one of those components. Well, that means you have to do 45 different injections to get these different calibration curves and get your response factors with some hopefully good accuracy. Well, with the Polyarc, if you take that same 9-component unknown mixture, you inject it, you get your quantification, well, you get better accuracy and you save about 97% of your time, right? So I had to make 46 samples versus 1 sample for the Polyarc. There's 45 calibration points versus no calibration points for the Polyarc. It took 23 hours versus a half an hour.
Paul, no one would shoot each sample, each species one at a time.
Correct. Yeah.
No one.
Correct. No one would do it. This would be the best way to do it, and you would get errors that are still worse than the Polyarc. So that was the point that I'm trying to make. So either way, you're going to save time. A lot of people will do one-point calibrations with multiple species, right? You're still going to save time, and you're still going to increase your accuracy even more.
Oh, you'll save time, but not 97%.
You can compute it. It's going to be high still, yeah. So I'm going to look now at 3 different case studies that show the use of the Polyarc reactor for things that we care about. The first one, as we promised, we're going to get into analyzing what we do and what we don't care about in terms of cannabis. Because you guys were interested in coming to a talk about cannabis, we wanted to throw this in there. No people were harmed in the doing of this study. So, when you're looking at cannabis, there are a number of different things, and there's a number of different labs that have opened up to look at these plants, which is actually a pretty difficult analytical problem in terms of the potency of what we're giving to people, the terpenes, the toxins, different pesticides, and different residual solvents that they use for extraction of the cannabinoids and other things like that. And so, since this is such a new field, there's really no standards for these sorts of things. So it's an interesting area for us to demonstrate the Polyarc as a way to do these things faster, especially when you look at the sheer number of compounds in a plant. So if we look at the potency, for example, there's 480 naturally occurring compounds in cannabis. 66 of those have been classified as cannabinoids. Of course, we don't understand the full realm of or ramifications of all these cannabinoids on our bodies. 9 of these compounds are typically tested for in potency testing. 3 of these compounds are easily available as traceable standards from companies like ResTech or Signal Aldrich. But they're very expensive. They have to ship them to you on dry ice overnight. And even for these 3, I think it was $300 to $400. So it can get very expensive when you're doing calibration standards for these things, especially if you wanted to do 66 compounds. So what I did with this was I looked at those 3 compounds, the CBD, THC, as you know, and CBN, which are really the 3 largest concentration compounds in cannabinoids. I ordered one of these traceable standards. I diluted it, and I looked at the, this is a log plot, and I looked at the intensity versus the concentration when I diluted it. So over about 3 orders of magnitude, from 22 ppm of these up to 1,000 ppm. And what we find is that the response factors are approximately 1 with an average error of about 1.3% for CBN. So the conclusion really is that you can look at these cannabinoids with high accuracy without using any calibration standards. You can assume a response factor of 1. And that's because we're converting everything to methane. So the second thing that I want to look at, again with relation to cannabinoids, is studying the pesticide residue that can be on these plants, or really any plants in general. So pesticides are designed to kill pests, and they're usually neurotoxins, right? It's one of the few things we add to the environment that are actually designed to kill living things. There's about 16,000 pesticides known. So the breadth of calibration standards that you would have to have, it's impossible, right, for anyone to do. There's about 10,000 that are approved by the EPA. Again, an impossible number to analyze. And about 64 of those have been banned by the EPA, but they still show up in a lot of foods. So there's a lot of scares about DDT and whatnot showing up in international foods. So what I did was took a look at, and this was actually work done in conjunction with the U of M, took a look at 22 organochlorine pesticides, and this is a snapshot of some of them, and we looked at them with the Polyarc reactor. And again, these are important for looking for pesticides in food. They show up in supplements, soils, crops, and water samples. And what we did is we looked at this 22 component mixture. Here you can see with the Polyarc and without the Polyarc. So you can see the chromatography is essentially the same with both. The areas, of course, are different, reflecting the different response that you're getting. And what we see is that the response factor is essentially 1 for all 22 of these pesticides. You see some scatter in the data and some uncertainty A lot of that is due to discrimination that occurs in the inlet. So if many of you use splitless inlets, those are actually one of the worst for discrimination in terms of what you inject may not be what you actually get out in your FID. And you do normally calibrate some of that out, but it can change. If you change settings, if you change gases, things like that can change the way that line or that inlet works. So what we did here was use a direct connect splitless injection to try to avoid a lot of that. And there's a good study on our website about how the inlet can actually discriminate some compounds. And that can affect your analysis. And so I want to come back to the point that Kim brought up with the change curve. And I'm assuming a lot of you here are early adopters by the sheer nature that you guys are in this room and learning about chemistry from crazy people like myself. But we actually need help moving into the early majority and getting adoption. It's not an easy proposition for any company. So we're here to sort of spread the news about this technology, but also ask that you guys can spread it within your organizations and hopefully connect us with early adopters there that are willing to try this out and learn about new ways to do things. So with that, I would encourage you to sign our sheet and take a pen if you haven't already done so. Schedule a presentation for your company. We're happy, especially locally, to go to these companies and talk about this technology and give demos. And also come see us at upcoming events. We are exhibiting and talking at PitCon, as well as AOCS for fats and oils, Minnesota Chromatography Forum. So a lot on our calendar, but it's been a fun year and a half, and we like to move quickly. So yeah, thank you all for your attention, and I'll definitely take questions.